welcome to this talk. I'm Soka, and the talk today is about TFLiteBEAM empowering edge devices with lightweight neural network inference framework. So the agenda for today covers those points. First, I'd like to briefly talk about what is TFLite and what devices it targets at and its advantages. Then we'll be building a bird classifier together, which includes most common steps to use this library. For this part, I will use Elixir for the example, but it is essentially the same for ERLA and other BEAM languages if they support using ERLA leaf libraries. After that, I will show you how to use Edge TPU for your neural network inference tasks, and a comparison between using CPU and Edge TPU. Of course, the actual result in your environment may be different depending on the size of the neural network and how many operations are supported by the Edge TPU hardware and your devices and other things. And next, I will show you 3 demos in Livebook, and if you have Livebook installed, then you can try and have some fun with those demos too. Lastly, I will talk about some future work in my mind, and if you have any questions, I'll be happy to answer them. Without further ado, let's talk about TFLiteBEAM. So, first of all, what is TFLiteBEAM? The first part of this TFLite stands for TensorFlow Lite, and it is a neural network inference framework developed by Google. It mainly has 4 advantages for those devices. Firstly, it has a small footprint. It sits around 10 megabytes compared to 500 more megabytes when using EXLA, or 700 more megabytes for torchx, making it an excellent option for edge devices and resource-constrained systems such as Raspberry Pi. Secondly, TFLiteBEAM is primarily optimized for mobile and embedded devices. It provides optimized model parsers and inference engines for those devices, delivering fast and low latency inference performance. Thirdly, using TFLiteBEAM also allows us to run models on Edge TPU like Google Coral, a hardware accelerator. In comparison, it is still nearly impossible to use any desktop GPUs on devices like Raspberry Pi, while adding a Coral Edge TPU as the hardware accelerator is relatively more accessible and practical. Lastly, as its name suggests, this library can benefit all BEAM languages as long as they have support for using ERLA leaf libraries. So now let's build a bird classifier together, and in order to do that, we first need to add this library to your app's dependency list. And for Elixir users, you can do this line to include TFLite Elixir to your app's dependency. And for ERLA users, you can use TFLiteBEAM. And for other BEAM language users, you can add TFLiteBEAM to your app's dependency list as long as your language supports ERLA leaf libraries. For this talk, I'll use Elixir as a language to build the bird classifier. So firstly, we define the bird classifier module, and then we define a function called load_module with one parameter, which is the path to your model. And then we can create an alias to TFLite interpreter, which we will use it to load our model by calling interpreter.new with the path to your model. After that, we can define struct for this module, and we will firstly add one field called model in the struct, and we will save the result to the model field and return the bird classifier for now. And then to use the neural network, we need to get the input tensor. To do that, we define another function called getInputTensor with the For the classifier struct to get all input tensors, we can use interpreter.inputs to retrieve all of them. It will return the indices of those input tensors. For example, if you have 2 or more input tensors, then it will return something like 5 and 10 in that array. For example, if you are using artistic style transfer, then you will have 2 input tensors. The first one is your original image, and the other one is your style image. So in that case, you need to set the correct data for both input tensors. As for this example, since we only have one input tensor, so I will simply add another field called input tensor in the define struct. And then I will use interpreter.tensor to get that input tensor with its index number. So if you do that in IEX, an interactive environment for Elixir, then you will be able to see that this tensor, TFLite tensor structure, it contains those fields. It has name, its index, and the shape. So the format of the shape means is using NHWC format, which means N stands for number of inputs, and H stands for the height, and Q stands for the weight of the image, and 3, which is also, or the C stands for number of channels of that image. So here it means that we need to pass a 3-channel image, and its size should be 224 by 224. Actually, you can see something like quantization parameters below. Those parameters are used for normalize the input image so that we can get the correct result from the model. So in order to do that, we can add another function called normalize input image. In this function, we first need to read the image using stb image.read file, and it will return an stb image struct which contains 3 fields, namely their data, shape, and type. And the data is the raw RGB values for your image, and the shape means the height, weight, and the number of channels. And then, since we need to resize the image to match the expected shape for the input tensor, we can pattern match the H and W parameter from the shape of the input tensor. And then we can try to resize the image using stbimage.resize. And then we can make predictions. So for that part, we can define another function called predict. It will receive 3 parameters. The first one is the body classifier, and then the image path, and the last one will be some options which we will use for post-process. So in this image, I first get the input tensor so that we can normalize the input image. And then I will do one more analysis for the TFLite tensor. And then we can use TFLite tensor.setData to set the image data for the input tensor. After that, we can call interpreter.evoke with self.model, which will do the actual inference for you. To retrieve the output, we can do interpreter.outputTensor, and we supply it with the self.model and the index of the output tensor. And then we will call the post-process function with the binary output and the options we passed to the predict function. As for the post-process, for this model, it will return a softmax array, and in that case, we will rename the first parameter to softmax, and the second parameter will be options. We will check the optional label file and the top K optional parameters here. And by default, it will be 3. It means that we will take the top 3 predictions from that result. And then, since the softmax variable is a binary, so we need to call nx from binary to create a nx array, and then we can do nx arc sort, and we can find the top 3 predictions for that image, and then we can take the top k of those indices. So lastly, we can create another function called toLabel, which will map those top k indices to its label with the label file if you have one. So if you don't have any label file, then we'll simply return the top k indices. Otherwise, we'll try to read the label file, and then we can map the label to each line. So basically, each line corresponds to a class. So now if you do this in IEX, then you will see the output will be those 3 bird species. And the first one is actually the ground truth for this image. So let's talk about how to add support for using Edge TPU. So to use Edge TPU, you need to add those lines to your code. It will enable Edge TPU support and try to find an available Edge TPU on the system for you. And it will upload the model to the Edge TPU, and then you can do everything as before, and you can get the hardware acceleration from doing that. So for comparison, here is a simple comparison using CPU and Edge TPU. For the device I'm using is a Raspberry Pi 3B. As we can see that for when using CPU, it's about 60 milliseconds per frame. However, when using Edge TPU, it's about 20 milliseconds per frame. So now I will show you I'll show you 3 demos. The first one will be artistic style transfer, and the second one will be the image classification, and last one will be object detection. Let's look at the first demo, artistic style transfer. In this demo, we'll be using 2 models, one for style predict, the other one is the style transform model. The first model takes one input image and it will extract the style vector for us. The second model will take 2 inputs. The first one is an content image and the other input is the style vector, and then it can generate the stylized image. So first we need some inlines, and then we need to download those testing data files, and then we can load the input image and the style image. Now we can proceed to the pre-process step, which we need to resize the style image to 256 by 256, and then we need to center crop the image. For the content image, it should be 384 by 384, and also we apply central crop to it. Also, we need to convert the pixel values to float 32 numbers. And then we can check the pre-processed images. Now we need to run the style prediction, which gives us the style vector. It should be a vector with a length of 100, float 32 values. And then we can run the style transform part. So for this part, we first load the model and then we feed the pre-processed content image and the style bottleneck data, which is our style vector, to the input tensor of that model. And then we can retrieve the output tensors, and then we apply some basic transform, and we change the pixel value range from 0 to 1 to 255, and then we can see the result. And then we need to run the style blending step, which calculates the style bottleneck of the content image. And then we can do a blend with a blending ratio. It should be a value between 0 and 1, depends on how much you want to get from the content image and how much you want to get from the style vector. So here I'm using 0.5 and apply the blending, then and we can see that and then we see the final result. Now let's have a look at the second demo, image classification, and we have some helper function that downloads some demo files for us, and then we just download the pre-trained model and its label, and then we choose the image that we want to classify which bird is in that image, and then we can do whatever we talked before. We simply get a new interpreter, and then we resize the input image, and then we use this predict function, and it will automatically fill the pass a tensor to it, and then we can do sort and take how many results we want, and then so this is our top K, and then we can generate a table for the final result, and as we can see, it has the same result. I also have an image classification module, and to this, it's really easy to use this module. It's called star with model file and or set label if you have one, and then you can call the predict function with the input tensor, and then with the input data, and then you can have some optional parameters such as top K and the threshold for the confidence, and then you can see the class ID, label, and score. So the last demo, object detection. In this demo, we also first download some data files, and then we load its labels, and we can load the input image. After that, we can do some pre-process, which resize the image, and then we can fill the input tensor and get the output tensor. For this model, we actually have 4 output tensor. They are the first one will be the boxes, and the second one will be the class ID. The third one will be the scores, and the last one will be number of detections. But here I'm ignoring the last tensor because we only need boxes, scores, and the class IDs. After we have those things, we can do the visualize part. In the visualization part, we simply plot some rectangles, and we also plot the label above the rectangle. And as you can see, we have this model successfully predicted the dog, the bicycle, and the truck. So okay, that's our demos. And now I will talk about some future work in my mind. So the first thing is that I want to make it easier to use. So now we have some modules such as image classification to automatically extract or necessary information for you, and it will fill the input tensors for you, and it will try to load the label file embedded in your model. However, maybe your model does not contain a associated file, so sometimes you still need to do that manually. So I want to make it more easier to use in the future. Secondly, I want to auto-convert models to TFLite, because when you are using NX to train your neural network model, then it would be great that if you can directly use that model with this library, so you don't have to convert your model to TFLite models somewhere else. It will simplify the process. And lastly, I guess some people may be interested in using multiple Edge TPUs. The reason behind that is the first time you load a model to the Edge TPU, it will need some warm up before it can become fast. That is how Edge TPU works. So if you only have one Edge TPU, then and you have two models, for example, you have one for image classification and one for audio recognition, and if you regularly switch those models on your Edge TPU, then the performance will be really bad and or not as expected. So that's why I want to try multiple Edge TPU support and also make that easier to use for you. So that's all from me today, and if you have any questions, I'll be happy to answer that.